Welcome to the 2009 Ralph Peck Award and Lecture. This is our second highest recognition, and this year we are honoring an outstanding geotechnical engineer once again. The award was established in 1999 by the Geo-Institute in honor of Professor Ralph B. Peck. The Ralph B. Peck Award is presented for outstanding contributions to the geotechnical engineering profession through the publication of a thoughtful, carefully researched case history or case histories, or the publication of recommended practices or design methodologies based on the evaluation of case histories. The 2009 Peck lecturer is Dr. Edward Kavazanjian, professor at Arizona State University. Our speaker tonight has provided valuable insights into the geotechnical aspect of constructed facilities that match the example set by Ralph Peck and the other distinguished recipients of this award. I would like to ask Dr. Kavazanjian to join me at the podium. Dr. Kavazanjian, in recognition of your case histories to evaluate the static and dynamic properties of municipal solid waste and hazardous waste and illustrate their application in landfill engineering, I would like to present to you this medal and this award. And now I'd like to expand a little bit on Dr. Kavazanjian's accomplishment. Dr. Edward Kavazanjian Jr. was born in 1952 in Long Beach, New York. He attended the Massachusetts Institute of Technology, graduating in 1973 with a Bachelor of Science degree in Civil Engineering. Ed was captain of the swimming and water polo team at MIT, was all New England as a water polo player, set school records in the 500 yards and 1,000 yards freestyle, and swam in the NCAA Division II swimming championships twice. Ed enrolled in graduate school in geotechnical engineering at MIT in 1973, working as a research assistant for Professor T. William Lamb. He received his Master of Science degree from MIT in 1975. In September of 1975, he enrolled in the PhD program in geotechnical engineering at the University of California at Berkeley. At Berkeley, Ed worked as a research assistant for Professor Jim Mitchell, receiving his PhD in 1978. Upon completing his PhD work at Berkeley, Ed received an appointment as an assistant professor of civil engineering at Stanford University. He held that position until June 1985, when he went to work with Parsons, Brinkerhoff, Quaid, and Douglas in New York City. In late 1988, he went to the Earth Technology Corporation in Long Beach, California, and then went on to MA Engineering Consultants in Los Angeles, and then worked for Geo-Syntec Consultants in Huntington Beach, California. At Geo-Syntec, he served as solid waste practice discipline leader and on the board of directors. Ed was also active in research and development at Geo-Syntec, establishing his reputation as a leading expert on seismic design of solid waste landfills. He co-authored guidance documents on seismic design of municipal solid waste landfill facilities for EPA and geotechnical earthquake engineering for FHWA. He was a visiting scholar at Monash University in Melbourne, Australia, an instructor at UCLA, and a professor at USC. In 2004, after 20 years in practice, Ed returned to academia as a professor at Arizona State University. He served as interim chair of the Civil Engineering and Environmental Engineering Department at ASU from 2006 to 2008. He has served on the ASCE Geo-Institute Board of Governors since 2005 and is currently the Vice President, President-elect of the Geo-Institute. He's currently chair of the National Academy of Sciences Committee on Geological and Geotechnical Engineering. Dr. Kavazanjian has given numerous invited state-of-the-art, state-of-the-practice, and keynote papers on landfill engineering, including the 10th Annual George Sowers Lecture and the 28th Martin S. Kapp Lecture. The title of the 2009 Ralph Peck Lecture is Pre-Design Evaluation of the OII Superfund site. Please welcome the 2000 Ralph Peck Lecturer, Professor Kavazanjian.
Thank you, Jean-Louis, and thank you for sticking around to hear my tale today. I've been incredibly fortunate in my education as a geotechnical engineer to be trained by some of the finest geotechnical engineers in the country or in the world. And I'm very proud, I'm honored to include Dr. Peck among those. In fact, I can trace my geotechnical heritage back to Ralph Peck along two lines, an indirect line and a direct line. And the indirect line is perhaps as important as the direct line. When I was a junior at MIT taking soil mechanics, the lab class was taught by Dr. John Garlinger, who was one of Professor Peck's students. And for some reason, I don't know, John took a liking to me and convinced me to take his graduate class in foundation engineering as a senior. I was a little wary at the time. I didn't have the prerequisites, but he assured me I would fare well, and so I took his foundation course, which he taught in the style that Dr. Peck is famous for, a case history class where each case history was written up on a single 8.5 by 11 page. Now, this was before word processors, but you could take a blank page and start in the upper left-hand corner and finish in the lower right-hand corner, printing as small as you wanted or as small as was legible, but nothing more than one page. John later wrote a recommendation for me for graduate school, which undoubtedly helped me get support as a research assistant at MIT. And so without that indirect link to Professor Peck, I wouldn't be here today. So John, thank you very much. Later, while I was in the PhD program at Berkeley, Professor Seed convinced Professor Peck, who had retired from University of Illinois, to come to Berkeley and teach not a short course, but an accelerated course in foundation engineering. And I was one of the 12 lucky graduate students who were selected to participate in that course. Dr. Peck came in for a week, and we met every day from 1 o'clock to 5 o'clock, and we did one case history a day. Same rules. That night we would go home, write up the case history as a single 8.5 by 11 page. He disappeared for a month and a half, then came back, and we did 5 more case histories. So we got a full 40 hours of instruction from Dr. Peck and 10 case histories. I never throw anything out, but I've moved back and forth across the country too often, and so somewhere buried in my garage are those case histories, and I have to tell you, I spent several hours going through my boxes trying to find one of those case histories that I could scan and put on the screen for you today, and unfortunately I was unsuccessful, but one of these days I'm sure I'll stumble across it. I also had the good fortune to work with Professor Peck on a project while I was a practicing engineer. We were working on expansion of a tunnel under the runways at Los Angeles International Airport, California Highway 1, Sepulveda Boulevard. And the runway was actually the roof of the existing tunnel, so it was a challenging project. And they'd had some recent problems tunneling under the runways. They were pushing a sewer tunnel under the runway. They had large sinkholes opening up as the ground surface as the tunnel approached the runway, so people were a little nervous about expanding this tunnel. We had a Board of Consultants meeting that Professor Peck attended, and One of the engineers on the sewer tunnel that had the sinkholes opening up was describing the ground conditions they encountered. And at one point, he started talking about perched water. Now, that seemed a little strange to me because these were very clean dune sands, no indication of any kind of interbedding. And so I started asking questions. And I asked him, well, he said the flow was 20 gallons per minute. I said, well, was that the initial flow or is that the steady state flow? He said, oh, that was constant. I said, constant for how long? He said, oh, as long as the tunnel was open until we got it sealed up. I said, well, was it all along the length of the tunnel? Did you encounter this in several locations? No, just one location. So I kind of exhausted my questions, was thinking in the back of my mind what the problem could be. And we took a break, and as we went to the bathroom, I cautiously approached Professor Peck, and I said, you know, that situation sounds a little strange to me. And Ralph turned and smiled at me, and he said, yes, Ed, it sounds like a broken pipe to me, too. All right, on with my tale. The Operating Industries Incorporated landfill, a unique urban hazard. This is a picture of the OII landfill, as we call it for short, in 1996. And as you can see, it's a rather imposing structure that sits astride a major freeway in a relatively densely populated area about 16 kilometers east of downtown Los Angeles. Landfilling at the site started in the 1950s in an old sand and gravel pit. It topped out in 1984. By 1985, my Armenian brethren, who had banked all the money for putting waste in the landfill, had disappeared, along with all the financial responsibility for closing the landfill. As an Armenian, I admire their business acumen. As an environmental and civil engineer, it's a little disappointing, frankly. But at that point, the site was put on the national priorities list, the Superfund list, and EPA deemed that site a unique urban hazard for a number of reasons. One reason is it was a hazardous waste landfill. Now, if you're in the landfill business, you know that if 99% of the waste in the landfill is municipal solid waste, but 1% is hazardous waste, then you're classified as a hazardous waste landfill. The hazardous waste landfill in this facility was a little bit more than 1%. 5%, 10%, but still predominantly municipal solid waste. It was piled up relatively high and steep, though. The north slope adjacent to the freeway rose 60 meters above grade and went another 30 meters below grade. It had an average slope of 1.5 to 1, and it sat right over State Route 60, the Pomona Freeway, which had anywhere between 4 and 8 lanes of bumper-to-bumper traffic at rush hour every day. If you think back about the slide I just showed you, on the south side of the landfill, there was a housing development that had built right up to the landfill. The back slope of the landfill was basically the backyards of the people whose homes were built adjacent to the landfill. And in fact, in 1987, as an interim measure, because there was a perception that the waste was creeping towards the homes, EPA constructed a mechanically stabilized earth, a reinforced earth tow buttress, supported on large diameter drilled piers, on the south side of the landfill to stabilize the waste until they could decide exactly what to do about the landfill. And then there was a relatively severe seismic exposure for this site that I'll talk a little bit more about in a minute. The north slope, average slope of 1.5 to 1, as steep as 1.3 to 1 between benches in some places. And if you look at the picture at the right, this slope really was that steep. I can tell you, when you were up there on a 12-foot wide bench trying to back up a truck, 60 meters above the freeway with a 1.3 to 1 slope below you, it's a little scary. You take your time when you're backing up. The south slope tow buttress I mentioned, you can see in the yellow circle the proximity of the homes in that corner of the landfill. The developer had built right up to the landfill property. So a 15-foot high reinforced earth wall was constructed by Woodward Clyde Consultants in 1987, or designed by Woodward Clyde, as an interim measure while the legal issues that always surround a Superfund site were being pursued. 1987, the Whittier Narrows earthquake occurred, and this earthquake was really a watershed event in terms of seismic hazard for the whole Los Angeles region. You know, California, everyone knows what the San Andreas Fault is, or most people do. It's what we call a transform boundary between the North American plate and the Pacific plate, and movement along that boundary is predominantly horizontal. However, in the Los Angeles area, the fault makes a little turn, and the seismologists and geologists refer to that as the Big Bend. And so while the fault displacement is primarily lateral along the fault, in the area that bends, some of that has to be accommodated in thrusting by movement perpendicular to the fault. And that thrusting creates the San Gabriel Mountains over there on the left, and the Sierra Madre Fault, which breaks up to the ground surface. But the Whittier earthquake occurred on a fault that was not previously recognized, and that had no surface expression. It was buried beneath the ground surface, or it had no surface faulting. There were lines of hills at the surface that were a surface expression that in hindsight were an indication there was something going on in the subsurface. But there was no faults, and up until that time, the seismic hazard had been based on faults that had surface expressions, that had faulting at the surface. Subsequent investigations following Whittier indicated that the LA basin is underlain by what we call blind thrust faults, faults that don't break the ground surface. And in fact, the greatest seismic hazard for downtown Los Angeles is one of these blind thrust faults with a capability of a magnitude of about 7, less than the San Andreas Fault, but much closer to the urban areas. And if you see over there on the left, on the ground surface, it says the Whittier Fault. The OII Landfill is right about the F in the word fault, very close to Whittier. In fact, Whittier caused some severe cracking on those benches on the steep north slope of the landfill, which of course triggered additional concerns over landfill stability. One of the good things that happened after Whittier is EPA's consultant at the time, CH2M Hill, installed some strong motion stations at the landfill, one on top of the waste and one down at the toe of the waste on what they thought was natural ground. And that turned out to be a very fortunate thing. The instrumentation really paid benefits further down the line in terms of evaluating the seismic performance of the landfill. And as I mentioned, Whittier also led to the identification of this blind thrust fault system that underlay the Los Angeles area. The particular blind thrust fault under the OII landfill was known as the Elysian Park blind thrust, or is known as the Elysian Park blind thrust. And that represented a significant increase in the already severe seismic exposure of the site. Well, here's an example of some of the cracking on the north slope. Now, this is actually from the Northridge earthquake. I don't have any slides of the cracking in Whittier, but I'm told it was very similar. You can kind of see the freeway in the background there to the left, and you can see that there was some very severe cracking on the north slope. Later on, when Professor Stokey was out there with a 20-ton truck vibrating the ground, when they were on that north bench, I conveniently had to stay in the office that day. I told them, take lots of pictures and send them to me, and I'll check back with you at the end of the day. So in 1994, my company, Geotechnical Consultants, was hired to do pre-design analysis for the landfill, or a pre-design evaluation, an evaluation in preparation for final design to help EPA decide exactly how they were going to close this site, what needed to be done. And some of the estimates of what needed to be done, including excavating the waste, cutting back to the waste to a tune of $400 to $800 million. And of course, the responsible parties were hoping we could come up with a cheaper solution. So our pre-designed scope of work had 9 work elements. Of course, the first thing we do is review and synthesize the available information on the site. We had a field investigation program, a laboratory test program. We conducted limit equilibrium stability analyses, a detailed seismic hazard analyses, taking into account the new information on the blind thrust systems to establish a design earthquake for the site, used that design earthquake in a seismic response and deformation analysis for the landfill, conducted a static deformation analysis to see what the landfill would look like 30 years from now. The responsible parties who were closing the landfill were also responsible for 30 years of post-closure maintenance and care of the facility. We had a specific investigation of the integrity of the toe buttress that was protecting those homes on the south, and then we had to issue a report of findings with recommendations for closure design. Now, I wish I wasn't as PowerPoint challenged as I am, because I wanted to bring a little audio in here of dueling banjos. But when we came on the job, the EPA had put together a technical review panel composed of 5 eminent engineers, Mary Ellen Hines and Ellis Kranitsky from the Corps of Engineers Waterways Experiment Station, Dr. Ed Idris, a former Peck lecturer and Terzaghi lecturer, Arvid Landva from the University of New Brunswick, who's perhaps the best known person in terms of the properties of municipal solid waste at that time, and Ray Seed from UC Berkeley. So we thought to ourselves, you know, we better have our own panel. We need some people who, one, the people on the EPA panel will respect, and two, who, if we disagree with the EPA panel, will give us some backup. So we put together our own panel, working for New Cure, which was the captive engineering company that had been formed by the responsible parties at the site to close the site. And our panel included John Christian, another former Terzaghi member, Terzaghi lecturer, Lloyd Clough, former chair of the State of California Seismic Safety Commission, the late Jerry Leonards, Jeff Martin, professor at USC, Jim Mitchell, and Rick Mitchell. And I say dueling panels tongue-in-cheek because the two panels worked really closely together to provide technical oversight and advice to us as we moved ahead on this project. And you know, Bill Marcusen at lunchtime talked about surrounding yourselves with first-class people. Being in a room at our quarterly meetings with our technical review panels with these people and my colleagues at Geosyntec, Rudy Bonaparte, Bob Backus, Gary Schmertman, and others, was a truly great experience. Well, we started collecting the important information from previous studies, the bottom contours of the quarry, so we knew exactly how deep the waste was. We later were able to verify that with some of the SASW soundings that Professor Stokey conducted on our behalf. There was an interim soil cover at the east end of the landfill where they had stopped landfilling for a short period of time that had an impact on the seismic response of the landfill. We documented that. Most of the hazardous waste was liquid waste that was disposed of in a practice known as co-disposal at the southwest end of the landfill. Nominally, they were supposed to have a mixing pit where they mixed 10 gallons of liquid waste with a cubic yard of soil. Interviews with the people who worked at the landfill at the time suggested they just dug a shallow pit, backed the truck up, and opened up the stopcock. And at that end of the landfill, there were seeps, and there was active leachate pumping going on. We collected the data on the construction of the tow buttress, complicated by the fact that the local Woodward Clyde office had had a flood and a broken pipe in their record room about 5 years before, so that data was a little sketchy, but we were eventually able to recover from a variety of sources documentation of how the tow buttress was constructed. Another important thing that happened after Whittier was a series of 3 lines of inclinometers were installed on the northern slope, on that steep slope. So we had, at that point, 7 years of lateral deformation data, creep deformation data on the behavior of the landfill. There were some previous geotechnical studies, notably one conducted by C.H. Hill for EPA. Tim Siegel, one of our GI members, was a lead engineer on that. They did borings and cone penetrometer soundings. We had strong motion records captured from those stations from 8 different earthquakes, 6 small nearby earthquakes, and 2 large distant earthquakes. The 1971 Landers earthquake, which is magnitude 7.1, 1991 Landers, magnitude 7.1, about 150 kilometers from the landfill. 1994 Northridge earthquake, magnitude 6.7, about 60 kilometers from the landfill. And those were very important sources of information for us, as you'll see. And then in 1992, there was a cover failure on that steep north slope after a very heavy rainstorm. So we collected all the documentation we could on that cover failure. One of the important things that came out of that collection of information was this plot on the shear strength of municipal solid waste. And when we first started working on OII, when I first started working in solid waste, which wasn't long before that time, there were papers in the literature that suggested that the shear strength of solid waste could be represented with a friction angle of 20 degrees. Well, you just have to look at a 1.5 to 1 60-meter high slope, and hopefully you'll recognize that 20 degrees is a little bit conservative for the shear strength of municipal solid waste. If it was 20 degrees, it would just be in a big pile on the freeway. So we went out and collected all of what we considered to be reliable information on large-scale testing of solid waste, and then did back analyses of stable slopes at 4 landfills with very steep slopes, including the OII landfill. So the little diamonds you see at about 50 kPa and 75 kPa, right on that 33-degree line, represent back analysis of the OII landfill. You'll notice 2 points below that line, 2 circles. That's the Lopez Canyon landfill, north of Los Angeles. We back calculated these shear strengths using a static factor safety of 1.1, since these were stable slopes. At Lopez Canyon, that slope had been subjected to, it was very close to the epicenter of the Northridge earthquake. It had been subjected to peak ground accelerations on the order of 0.4 to 0.5 G in the earthquake. So we felt 1.1 was a little conservative for that site. Those slopes showed no signs of any long-term deformation or cracking. So we were comfortable having those 2 points below the 33-degree line. And this shear strength envelope is now widely used to represent the shear strength of municipal solid waste. So that was one of the first contributions to practice from this project. We had a very detailed field investigation. As I alluded to, we conducted a spectral analysis of surface wave survey. We hired Professor Stokey and his team at University of Texas to come and do the survey. We installed 3 34-inch diameter bucket auger borings to depths of up to 155 feet. Now, this isn't cheap. We would have liked a few more borings, but we were able to convince the client to pay for 3 of them. And we did detailed waste characterization of the waste recovered in the bucket augers. We conducted in-situ unit weight tests on the way down, and we did some video logging of the holes to get an idea of the structure of the waste. We also did a large test trench at the surface of the landfill, 20 feet deep, 20 feet wide, to categorize the structure of the waste, and then we also backfilled it with gravel to get an idea of the unit weight. We weighed the waste that we took out, we backfilled it with a calibrated gravel, like a big sand cone test, and used that as an estimate of the unit waste. We conducted a condition survey of the toe buttress and a very detailed investigation of the shear strength of that cover soil on the north slope. This is the field exploration plan. The solid lines you see are the SASW surveys. You'll note we did do a couple on that steep north slope over there on the right-hand side, but I think, and Ken can correct me if I'm wrong, the health and safety people at the landfill came running out and started waving their arms and waving off the truck, which I'll show you in a minute. 3 large diameter borings. I'll just note that boring BA3 over on the right is at the north end or the east end of the landfill, where it was almost all municipal solid waste, no indication hazardous waste or liquids were ever disposed of there. BA2 in the lower left is the so-called sweep area, southwest area, where the liquid waste was disposed of and where there were seeps on the surface after a heavy rain. And then BA1 was kind of in a transition zone between the areas where liquid was disposed of and between the area where no liquids were disposed of. This is the truck that was used for the SASW surveys. This is a Vibra-Sice used in the oil exploration industry. I think it's the model for the big shakers that Professor Stokey now operates for the NEAS, Network for Earthquake Engineering Simulation. I think it weighs about 20 tons. And you can imagine having that on a 15-foot wide bench on that 1.3 to 1 slope and having it vibrating up and down. I admire Professor Stokey for pursuing his pursuit of science and knowledge in that effort. Well, fortunately, SASW, I think people have generally accepted now. In 1996, I think it was still considered a relatively new technique. But where the seismic station was on top of the landfill, a previous consultant had put in a deep boring and had made downhole shear wave velocity measurements and measurements using the OII suspension logger, which again was a relatively new technique at the time. So we were able to compare the shear wave velocity profiles from SASW to these other 2 techniques, and as this figure demonstrates, we got very good agreement, and so we were able to move ahead using the SASW data with good confidence that it gave us results that were comparable to other geophysical techniques. One of the things we use the shear wave velocity data for, besides the seismic response analysis, and besides trying to determine what the depth of the waste was was to plan our sampling intervals. So we took the 27 shear wave velocity profiles we did around the landfill and we averaged them. We did a statistical analysis. We got the mean trend, which is the solid line, and the mean plus and minus 1 standard deviation trend. And then we planned our sampling intervals to sample areas where the shear wave velocity, as measured in the site-specific shear wave velocity measurements, was below the mean, close to the mean, minus 1 standard deviation, equal to the mean, and greater than the mean, with the belief that this would then be reflected by differences in the characteristics of the waste. And by doing this, we would be sure to get a broad variety, or the complete spectrum of the type of waste disposed of at the landfill. So if you look at this figure, we took 6 bulk samples. We had 6 sampling intervals in each of the boreholes. So we took 18 sets of bulk samples. At each location, we did an in situ unit weight test to capture the unit weight of the waste. And then these were the samples we used for our laboratory testing program. So the intervals marked LV were the low velocity samples, MV were the median velocity intervals where we sampled, and HV were the high velocity intervals. And so we had 2 of each in each of the 3 borings. The borings were done with a 34-inch diameter bucket auger, the big bucket auger. Now, typically we use these things in Southern California for slope stability investigations. We do, in the weak sedimentary rock, we put the big bucket auger holes in, then we put our geologists in a little cage, we send them down the hole, and they map the strike and the dip of the strata, and they love it. They get real excited about that, in fact. But for some reason, they didn't want to go down these holes. I'm not sure why, you know. We had trouble convincing the geologists to go down, but as the waste came up out of the hole, we would empty it in this metal bin, and then our field engineers would do some detailed logging of the waste. We actually had to develop a waste classification system. There is no standard waste classification system for solid waste. So we went through the literature and collecting the best practices, we put together this field classification scheme for the waste, whereas the waste came out of the bucket auger. It was classified in terms of its moisture content, damp, wet, standing water in the hole, dry, wet, or standing water, its compaction based upon how it fell out of the bucket, the state of degradation based primarily on newspapers and printed material. In fact, over in the boring in the dry area of the landfill, we pulled up 2 pristine tickets to a 1956 presentation of Cinderella in downtown Los Angeles. I wanted to go back to the box office and get a refund, but they told me that theater had been torn down about 15 years before and quite possibly now resided in the OII landfill. We also, of course, categorized the composition of the waste. We had 13 compositional categories, including, of course, the other category. And sometimes we were able to capture the structure of the waste, whether it was layered or the solid waste was encapsulated in a soil matrix, although I have to admit, most of the time we used category 5, which was indistinguishable. So this is an excerpt from one of the field logs, the time, the depth, the temperature. As the waste came out of the bucket auger, our field engineer would put a thermometer in the middle of the waste and capture the temperature of the waste, moisture content, compaction, degradation, structure, then some notes on the composition and other comments based upon what was encountered in the boring. Then we would compile that information. So for instance, here's the information on waste degradation from our 3 borings. You see this general trend of increasing degradation with depth, but you also see that it's a little bit scattered, that sometimes at very deep depths, at the dry end of the landfill, we would have waste that showed no sign of degradation. Other times at shallow depths at the wet end of the landfill, we would see a high level of degradation. And that's very consistent with our knowledge of waste degradation, particularly in arid and semi-arid areas where the degradation is limited by the availability of moisture. So where we had moisture, we had heavy degradation. What we also encountered, and that's reflected in the scattered nature of this plot, was that the waste was very cellular. We would hit pockets of standing water at shallow depth. We would punch through those pockets, and then we would encounter a dry zone with relatively undisturbed waste. So very inhomogeneous character to the waste in the landfill. Waste temperature is another important indicator of degradation. Anaerobic degradation produces temperatures on the order of 50 degrees centigrade. Aerobic degradation produces temperatures on the order sometimes as high as 80 to 85 degrees centigrade. If you look at this degradation plot, you'll note, I'll note BA2 is down in the wet zone. That's where we had a lot of moisture, and that's where we had the highest temperatures and the greatest degradation. BA3 was at the dry end of the landfill, and that's where the temperatures were the lowest, but still elevated. You go down in the hole, and it's 60 degrees centigrade, about 150 degrees Fahrenheit. So the landfill was cooking. The waste was degrading, clearly. We developed an in-situ unit waste test that we've since used at several other landfills that, again, was basically a big sand cone test. We would auger the waste over a predefined interval of the borehole, typically 3 to 5 meters. The waste that came up in the bucket auger over that interval would be weighed at the landfill scales. We would put a tremie pipe in the hole and tremie in a calibrated gravel, a uniform gravel that we had previously calibrated to establish a unit weight at which it would fall into the hole at. We would weigh the amount of gravel put into the hole, weigh the truck beforehand, weigh the truck afterwards, and take the difference. And we would use that information to back calculate the solid waste, unit weight. And as I say, that was some great field data for us, and we've since used that at several other landfills. And there was a paper that appeared in the ASCE journal about a year ago on the unit weight of municipal solid waste that talks about this procedure and presents the results from some of our landfill investigations. These were the results at OII, pretty scattered. You know, typically you would expect the unit weight to increase with depth. If you had a uniform material, it would increase with depth. So the random nature, somewhat random nature of these unit weights reflects the variability in the waste. For engineering purposes, we then we also show the unit weight we got in that large test trench at the surface. For engineering purposes, we characterize the unit weight, 15.7 kilonewtons per cubic meter. That's about 100 pounds per cubic foot for those of you who still like to work in the imperial system. Importantly, that's significantly higher than the unit weights that people used and still use in practice today. And whenever I review these landfill designs, you know, it's a battle. People go in at 55 pounds per cubic foot, and I say let's use 100, and we usually wind up about 85 to 90. But every time we go out and measure it, we tend to find it up in this range, it seems. In fact, what we did working with Professor Stokey is we correlated the shear wave velocity to the unit weight. We got a pretty good correlation. And so we used that correlation to take our shear wave velocity profiles and translate that into a unit weight profile for the landfill. And so again, the dark line, the dark squiggly line is the median value. And here we're also showing the mean +1 standard deviation, the mean -1 standard deviation, and then the absolute maximums and minimums based upon this correlation. The very dark line on the left was a unit weight profile we had proposed about 3 years before without any data. That apparently is still widely used. In fact, when we presented some of this unit weight information in Europe and said, you know, this old 1995, Kavazanjian et al. 1995 is not reliable, several of my European colleagues came running up and said, no, we like your unit weight profile. Please don't change it. But this is the new story that I'm sticking to. We did downhole video logging of each borehole. We hired an oil well logging company to come out with their camera and do a downhole video log. And so I thought I would take a trip down the rabbit hole with you. And so let's see if we're lucky here and if we can get the video to work. And so here we are, taking a little trip down a 34-inch diameter bucket auger borehole inside the OII landfill. And for the life of me, I can't understand why the geologists didn't want to go down that hole in a cage. Huh? And the mist you see in the background is condensation. Remember, the temperature inside the landfill is on the order of 60 to 65 degrees, very moist due to landfill gas. That was fun. Let's do that again. I think I got to cue it up again. And you can see the structure of the waste, the relatively horizontal orientation of the fibrous materials, the fibrous waste sticking out of the sides of the borehole. That's about a 10-meter segment. The numbers in the middle of the screen, I should point out, that's the depth in meters. We logged down to about 40 meters in the 3 boreholes. Well, we took that waste and we did some testing. We constructed an on-site laboratory to test 18-inch diameter, 454 millimeter reconstituted samples. Our original intent was to try and recover undisturbed samples. When the cost of recovering undisturbed samples, when our estimated cost of the equipment got to about $500,000, and we still hadn't figured out how we were going to extrude the samples from the stainless steel cylinders into the testing devices, our client said, come up with a better idea. So we decided to go to reconstituted samples, reconstituting them to the field densities, and then testing them. We had a consolidometer, a direct shear device, and a cyclic simple shear device. Building that laboratory in itself was a major accomplishment. Professor Landva, who at the time was the leading authority on large-scale testing of solid waste, told us it would be 3 to 5 years before we would run our first test. And the Geosyntex staff in Atlanta, led by Bob Backus, with help from Rob Swan, Dennis Vanderlinde, designed and fabricated that equipment in less than a year and got the first test going. And that in itself was a major accomplishment. This is our cyclic simple shear device, our pride and joy for getting the dynamic properties of the material. I'm happy to say it now resides in my laboratory at Arizona State University. You know, a Superfund project like this, when the project's over, the committee that manages the work, the 17 responsible parties in this case, they dissolve and they had no use for the equipment. So they told me that for the salvage cost of the equipment, I could have it. And first I purchased it when I was at Geosyntex and went in the Geosyntex lab. When I left Geosyntex, they donated it to the university for tax deduction. This frame itself weighs about 6 tons. And as one of my colleagues said to me, it's a good thing we built it before the price of steel went up. So this is a cyclic simple shear device. The top is fixed, the bottom is on a carriage that slides back and forth with a double-acting piston that typically we put a sinusoidal load in, but you could even put a random earthquake load in if you were so inclined. After every lab test, we did detailed characterization of the material. We would take the bulk sample, break it up into its constituents, and sort it into paper, plastic, metals, glass, and then what we called soil and soil-like material, because it was a fine-grained material, but there was no guarantee it was soil. In fact, a lot of it was degraded waste. And one of the surprises for us on this project, and it's been repeated on many other landfills, was the large percentage of soil and soil-like material that's in the waste. And to a certain extent, it reflects the amount of soil that typical landfill owners put onto the landfill, but it also reflects the state of degradation of the waste. And I think at OII, the average amount of soil and soil-like material was on the order of 80% by weight, less by volume, of course. And we had some samples that were as much as 99% soil and degraded waste material, representing down from the wet end of the landfill and representing a very high state of degradation. And that had an impact on the properties, as I'll show you in a minute. These are the consolidation test results. A little bit all over the map. The one thing I'll point out is that on unloading, there's very little recoverable strain. Most of the strain in loading is irrecoverable. So we do the loading and then the unloading cycle, and you can see from that bottom plot, those bottom plots, very little vertical strain on unloading. One of the things you can do with a unit weight, with a consolidation test, is you can kind of turn it on its side and basically present it as a unit weight versus depth profile. We were a little bothered by the fact that our in situ unit weight test didn't show a consistent trend of increasing unit weight with depth. So we took our consolidation tests and we plotted them as the unit weight rather than the vertical strain versus the normal stress. So each one of these curves would represent a profile of unit weight versus depth, essentially, for a given waste composition. And if you take an average unit weight of 100 pounds per cubic foot, you take the vertical axis on the left-hand side, just knock off 2 zeros. So 5,000 PSF is 50 feet, and 10,000 PSF is 100 feet. And so you can see if the waste composition stays constant, you do get a nice increase in unit weight with depth. And that's just another indication of the fact that the waste within the landfill itself was very variable, which is why we got that high variability in unit weight as we went down into the ground. These are the direct shear test results. What I'll call your attention to here are the numbers in the boxes. And the numbers in the boxes represent the percentage of distinguishable solid waste in the material. So if you subtract that from 100, that'll give you the percentage of soil and soil-like material. So down at the bottom, at our lower bound envelope, which had a cohesion intercept of 43 kPa and a friction angle of 26 degrees, you'll see two numbers, 1% and 7.8%. Those were samples when between 92 and 99% of the material was soil or degraded waste. And those were the lowest strength materials. The dashed line on the upper bound, you'll see a 90%. And that was certainly the sample that had the greatest amount of refuse in it. So again, there's some scatter in this plot, but there does seem to be a general trend between the strength of the material and the amount of soil and soil-like material versus the amount of waste material. We just completed a collaborative research project with the University of Texas at Austin and Berkeley, where we reconstituted samples with different proportions of refuse and soil-like material that basically confirm this trend in the material behavior. The cyclic test, of course, what we want are the hysteresis loops. From the area of those loops, we get the damping. From the secant through the tips of the loops, we get the modulus, the strain-dependent modulus. So we would typically test at 3 different strain levels and then monotonically load the sample to failure. The results of the, so the lowest resolution we could get in that in this cyclic simple shear was about 0.1% shear strain. Typically, when you plot this stuff for earthquake engineering, you want to go down to 0.001% shear strain. So the testing gave us the high strain properties of the material. On the left-hand side, we're plotting the normalized shear modulus. The shear modulus we measured in a test divided by the maximum shear modulus, the small strain modulus. The right-hand side, we're plotting the damping ratio. This was only part of the story, and we needed to fill in the rest of that curve in a small strain range. And that's where the strong motion records came in. And without them, we probably would have been lost. So these are the 2 strong motion stations shown with the cross-sections of the landfill. I think when I first mentioned the strong motion stations, I said, or I should have said, that the one at the toe of the landfill was ostensibly placed on bedrock. And that's part of this story. You'll see here it shows it placed on fill. Originally, we assumed that that station was placed on bedrock. And in fact, some of the previous analysis made that same assumption. This is a plot from a paper by Tim Siegel, Don Anderson, and others at CH2M Hill that was in the Slopes and Embankments Conference in 1992, where they're looking at spectral amplification of the earthquake motions. They take the earthquake time history at the base station at the top of the landfill. They do a Fourier analysis. They break it down into sine waves. And then at a given frequency, they look at the ratio of the sine wave that represents the motion at the base and the sine wave that represents the motion at the top. And that ratio we call the amplification ratio. If they're the same, it'll be 1. Here you see spectral amplification on the order of 10 or 11 at about 1 second. That 1 second represents the natural frequency of the waste mass. And in fact, if you take the average shear wave velocity from Professor Stokey's soundings and you pop it into one of my favorite formulas, that the natural period is 4 times the height of the landfill divided by the shear wave velocity, you come out with exactly 1 second. So this was some work done by CH2M Hill, but this work assumed that base station was on bedrock. Another typical plot you see in earthquake engineering to represent amplification is representing the amplification at the ground surface for different soil conditions versus the theoretical amplification of a hypothetical bedrock at the ground surface. If you had bedrock at the site, you'd have a 1-to-1 line here, a 45-degree line. And the open squares here represent the point you get if you assume that the base station at OII was on bedrock. And it doesn't show any amplification. In a couple of cases, there's no attenuation. The motion was the same. But in other cases, the motion at the base station was significantly less or significantly more than the motion at the top of the landfill. The problem is when we look at those base station motions, they were much higher than they should have been. For instance, the open square that's highest on the plot represents the Northridge earthquake. At that base station, it was about 0.25 g, 0.25 the acceleration of gravity. If you used a standard earthquake attenuation relationship and you took into account the magnitude of the earthquake and the distance, that should have been about 0.1 g. So something strange was going on. The motions at the base station were much higher. There were a couple of different theories for that, but eventually we found documentation of the fact that at that end of the sand and gravel pit, there had been a landslide. And there was commercial development just beyond that site, so they had gone in and put in a compacted fill buttress, and the base station was on the compacted fill buttress. Well, so how do we account for that in the analysis? We do something we call deconvolution. We take the motion in the bedrock at the base station, we run a one-dimensional analysis using shake. We take it down through the fill back into the bedrock, then we move over to the side and we take it up through a bedrock column to the ground surface. And we say that's what the motion should have been if there was bedrock at the site. When we use that as the reference for the plots, all of those open squares move over to the left to the point where we are showing amplification at the top of the landfill. And in fact, it looks very much like a curve that Les Harder developed for amplification at earth dams. What does that mean? That means you could have a 0.1 G acceleration at the base of the landfill, which according to EPA is the threshold over when you need to do a seismic analysis or not. With amplification potential at the top of the landfill, you could be looking at 0.3 to 0.35 G, 3.5 times what you're measuring at the base. That's pretty significant. So after we did the deconvolution, we wanted to do a back analysis to get the small strain properties of the waste. So we built a finite element model of the landfill using Quad 4M, and not just because Professor Idris was on the review panel, but because we thought that was the best program available at the time. Putting in shear wave velocities based on Professor Stokey's survey. You see a dark line in the middle there. That's the interim soil cover that I mentioned, and that affects the seismic response. Some of the earthquake waves bounce around between that interim soil cover and the surface, and that has a significant influence of the fact. We've got on the response. We've got the fill modeled over there on the right-hand side, and then we do back analysis. So something you learn when you do back analysis is you can have too much data. If we only had one set of strong motion records, the back analysis would have been a piece of cake to find the best fit properties. Unfortunately, we had 8 sets of strong motion records. So I could get good agreement with one set, and when I use those same properties with another record, it was miserable. So it was a major task to find the balance between those 8 sets of records, and for that I'll credit Nevin Matasevic at Geosyntek, who did yeoman's work on these back analyses. These are just 2 typical records. We had, and besides having 8 records, we had 2 points of reference. We had the station on the bedrock, on the fill, and we had the station on the top of the landfill. If I matched the station on the fill, it didn't necessarily match at the top of the landfill. If I matched it at the top of the landfill, it didn't necessarily match at the fill. So it was a real balancing act to optimize the properties. So these represent 2 of the comparisons with our best fit properties. On the left-hand side is the match at the base of the landfill, the solid line being what we predicted, the dashed line being what's measured, on the right-hand side being at the top deck. And, if you look at all 8 records together, if I put them on the screen, you wouldn't see any resolution. It was a pretty good balance. Over all the period ranges, sometimes we were low, sometimes we were high, but on the average, we were matching the response of the landfill. Well, if we go back to my modulus and damping plots, the dark solid lines represent our best fit properties from the back analysis. And from our laboratory tests, we developed a family of curves to represent modulus reduction and damping, upper bound, average, and lower bound. But based on the back analysis, then, our best estimate was that upper bound modulus reduction and lower bound damping curve. And those 2 are compatible. The upper bound modulus goes with the lower bound damping. So we looked at that full range of curves in our analysis, but our best estimates were based on the upper bound modulus and the lower bound damping curves. Well, we also did extensive limit equilibrium analyses. We did static analyses to get the static factor of safety. In those analyses, we considered the fact that the waste is likely to be weaker on a horizontal plane than on a vertical plane or on a plane that cuts across the horizontal because of the preferred horizontal structure of the waste. And also because we had these horizontal soil layers of daily and interim cover in the landfill that could also represent planes of weakness. We used perched water levels. The maximum height of perched water we encountered in our exploration was 8 feet. So in fact, every time we looked at a horizontal failure plane, we would perch 8 feet of water, put a hydraulic head on that plane as part of the analysis. And then, because of the concern over those north slopes, we did veneer stability analyses for the cover. Now, for the seismic analysis, we also then would evaluate what the yield acceleration was for a variety of different failure mechanisms. In the static analyses, the failure surfaces through the waste mass were all satisfactory. I think the lowest factor safety we got, even on that steep north slope, was on the order of 2, 1.9 to 2. So we weren't worried about the static stability of the waste mass. However, the cover veneer stability was problematic. As you can see, it depended on the thickness of the soil cover as well as the slope. And on those steep areas of the north slope, 1.25 to 1.5, the 1.3 to 1.5 to 1 slopes, it was below what we considered acceptable, below 1.5. And this is without any tension cracks or tension cracks full of water. So you put in the potential for cracking, and in a rainstorm when a crack fills with water, and these factors of safety were dropping pretty close to 1. The pseudostatic analysis gets a little complicated. Probably the biggest mistake I see when people do a seismic analysis and when they do a pseudostatic analysis is they look for the surface with the lowest yield acceleration and they say, aha, that's the surface that's going to be critical in the earthquake analysis. Not true. The surface that's critical in the earthquake analysis is the one where the ratio of the yield acceleration to the average acceleration from the earthquake is the largest. And that average acceleration from the earthquake depends upon the size of the failure mass. So we did a series of circles from different benches, moving the circle progressively back, making it bigger and bigger. The bigger circles would have a lower yield acceleration. The smaller circles have a higher yield acceleration, but they also have a higher earthquake acceleration. So you can't say a priori which one is more critical. You need to look at all the different cases when you do the analysis. So we looked at a family of circles. We looked at families of wedges. From each bench, we took a series of wedges to get the yield acceleration. And we have to compare that to the seismic loading. Well, the seismic loading turns out to be governed by these blind thrusts. So this is a picture of the known earthquake sources in the vicinity of the landfill. You see the landfill there in the middle, and you see it sits right in the middle of the Los Angeles segment of the Elysian Park blind thrust. The fault was estimated to be 11 kilometers directly below the landfill, capable of generating a magnitude 6.9 earthquake. And using the available attenuation relationships, that meant we would have a 0.7 G, 0.69 G acceleration at the ground surface for the maximum credible earthquake, the largest expected earthquake in the known tectonic framework, which is the design earthquake for hazardous waste landfills in California. So that was our design event. We took a family of 5 time histories to represent the design event. We put them back into a finite element model. We took the ground surface records, we took them down at depth with shake, and then we took the shake motions and put them at the base of our model and brought them back up through the landfill. And then we calculated the average acceleration for the different blocks that represented our pseudostatic yield acceleration blocks. So you can see some of the blocks here concentrated on the north slope. We had different blocks with the different veneers within the cover. We had wedges and circles. We had shallow wedges and deep wedges. And then over on the right side, the south side of the landfill, we had a global surface through the toe buttress, and we had a very local surface through the toe buttress. I'll call your attention, the numbers on this slide represent the actual peak ground accelerations from the response analysis for one of the earthquake records. We had 5 different records, but you'll notice that it gradually increases on the left side, on the north side, as we get to the top of the landfill. It was 0.7 down near the base. That makes sense because the bedrock acceleration is 0.69, 0.8 G at the top. But look over at the right side. The highest acceleration in all our analyses was the toe buttress. And that's what our structural friends would call hogging the load. The toe buttress was a very stiff element within this very soft and ductile waste mass. So when this thing starts to shake back and forth, the stiff member attracts the most load. So the peak accelerations in that toe buttress were always the greatest, not necessarily good news for the people living on the south side of the landfill. To bring it all together, we take the average acceleration time histories in those different blocks. We run it through a Newmark analysis. We get this curve of displacement versus yield acceleration. Then we go back to our pseudostatic analysis, take the yield acceleration, go in and pick off seismic displacements. And our seismic displacements, almost all of them were in the range of 3 to 12 inches. And based on our experience with past earthquakes and supported by our technical review panel, that was considered acceptable. 12 inches of seismic displacement in this large ductile waste mass, 12 inches of calculated seismic displacement, I should mention that the type of analysis we're doing is generally conservative and generally overestimates the actual seismic displacement, was considered acceptable seismic performance for this and the maximum credible earthquake. We used to say, well, all the bridges will fall down and none of the hospitals will be operating, but our landfill will still be standing. We also did a very sophisticated static finite element analysis to try and predict the 30-year performance of the final cover. The concerns there are maintaining drainage grades and cracking of the soil cover on the north slope, and also to try and predict the 30-year performance of the toe buttress, both statically and what would happen if, after 30 years of settlement, all of a sudden the toe buttress got hit by the design earthquake. So we superimposed the static deformation after 30 years, or we superimposed the seismic loading on top of the static deformation after 30 years. For the static analysis, we used a time-dependent Cam Clay plasticity model. We used a computer program called PISA, developed by Professor Morgenstern and his students. Paul Sabatini at Geosyntac was most responsible for this analysis. The program includes secondary compression or volumetric creep and deviatoric creep or drain creep. So we did back analyses of the measured deformations of the landfill, including those inclinometers, to get some best fit properties to plug into this model and then to predict forward for another 30 years. We also had a 1980 era load test where they loaded up one of the benches as much as they could and measured deformations to calibrate our model on. Unfortunately, the calibration wasn't particularly successful. So here you see vertical and lateral displacements at one of those sections where we had inclinometers. The diamonds represent the actual measured displacements, which are pretty non-uniform and inhomogeneous. And we could match, we could fool around with the properties. This shows 3 different sets of properties that we used to try and match those displacements. We could match the horizontal displacement, but then we wouldn't match the vertical. We could match the vertical, but then wouldn't match the horizontal. We could match the horizontal over one portion of the record, but not over the entire section. So I have to say that we were probably most disappointed in the results of these analyses. But I think we did learn from that waste deformation is actually very inhomogeneous. And different parts of the landfill at different times are decomposing. It's a very non-uniform process, and that leads to very non-uniform deformations. One of the reasons we did the deformation analysis is we wanted those 30-year deformations to impose on a toe buttress. So let's jump over to the toe buttress. Global stability looked good, factor safety 2.6. So our concern was internal stability, the strength of the geogrids. And to analyze that, we used a finite element program from Berkeley called GeoFEEP. This analysis was done primarily by Jorge Zornberg. And we imposed our projected 30-year deformation on the toe buttress and then subjected it to pseudostatic seismic load using the seismic coefficients from a seismic response analysis. Except we didn't use the deformations from the finite element analysis. I should mention that there were 2 toe buttress sections. There was one section where it was supported on drill piers because the ground dropped away as you moved away from the landfill. And that's where stability was believed to be critical, so when Woodward Clyde designed this buttress, they put 3-foot diameter drill piers filled full of concrete at 6-foot spacing. So this is a deep foundations Congress. I guess it's good that I have some deep foundations in here, huh? Over on the right-hand side, part of the section, the ground was level, and that wasn't quite as critical. This is the layout of the toe buttress showing the extent of the pier installation, 2 different sections where we installed piers, and then showing 8 sections where we had measured deformations. We had survey data on the deformations of the toe buttress from 1992 and 1997. So we took those 2 sets of measured deformations, and being good geotechnical engineers, we put them on a semi-log plot and drew a straight line through them and projected out to 30 years. We got a couple of points there that show heave. I'm not sure I believe that data. Most of the points show relatively modest settlements, relatively modest, 3 feet, 4 feet. And then the one station, Station 8, shows up to 6.5 feet of settlement if we project on a straight line plot for 30 years. And in fact, that's what we used for design. So we subjected our toe buttress to 6.5 feet of differential settlement between the top and the bottom, and then we put the design earthquake on it. So here's the section showing the concrete pier, which we assume pinned the head of the toe buttress, so there was no settlement. Then we those measured surveyed settlements were at the back of the slope where you see that little V ditch. So we imposed lateral displacements at the bottom of our finite element mesh until the surface displacement at that point matched what we measured. Then we continued to increase the deformation until we got 7.5 feet of settlement at that point. And then we superposed the seismic loads as a pseudostatic load over the hatched area, which our limit equilibrium analysis indicated was the critical wedge. And that resulted in tensile strains in the geomembrane, in the geogrid, which we then compared to the strength of the geogrid. But the question was, what strength should we use for the geogrid? It will have been undergoing creep for 30 years at that point, so what was a reliable strength to use? So we did some creep tests on geogrid, and this was the actual geogrid used in construction of the toe buttress. The geosynthetic companies, God bless them, they archive samples when they have a major project like this. So we were able to contact Tensar and get samples of the actual grid that was used in construction of the toe buttress. So we took those grid samples and we did about 4 or 5 of these tests. We did a wide width tensile test, an immediate short-term loading test to get the solid line, and then we would do creep tests. I think the longest creep test was up to 6 months. We had a project schedule to meet. But the important finding was that when we reloaded it after creep, much like soils, we had an initial stiffening of the response, but eventually it essentially came back to the static stress-strain curve, the immediate loading stress-strain curve. So, and you'll notice here then that we would get out to strains on the order of 15 to 20% without rupture of the geogrid. Well, this slide summarizes the deformations from our analysis. We built up the geogrid, we built up the toe buttress in sections, so we were predicting strains at the end of construction. We had the current condition for the current measured settlement, the final differential settlements after we put that 7.5 feet of differential displacement on it, and then the earthquake loading. And so you can see reinforcement level 9 is the critical level with an axial strain on the order of 10% in the geogrids. In fact, I think I have a slide with a seismic coefficient of 1G, which is what we used, because that's what our finite element analysis indicated. We were getting strains on the order of 9% in that geogrid. We were running the test out to 20% without rupture, so our interpretation of that was that the performance of the toe buttress was adequate, even if after 30 years of differential settlement, it got hit by that design earthquake. All right, well, we're getting near the end here. Findings and recommendations. We had to pull all this stuff together and make some recommendations for design. The first finding, and a very significant one, was that the waste mass itself met static and seismic stability criteria. And as I mentioned before, that was important because the remediation costs, if it didn't, were estimated to be between $400 and $800 million. So I think we earned our fee right there. And thanks for that, we were allowed to bid competitively on the next project for these owners. Large static deformations are expected, and so we told the owner, you need to be prepared to do continuous maintenance over the next 30 years. Kind of a no-brainer, but those cover soils are going to crack. You can't let those cracks stay open. If they fill with water in a storm, you still have a significant chance of veneer failures. We had the freeway down below, so and you're continually going to have to adjust the drainage grades. Your gas wells are going to break all the time, so you're going to need a full-time maintenance staff addressing these issues. The toe buttress should maintain its integrity. Even after 30 years of settlement plus seismic loading, we were confident that the toe buttress would maintain its integrity. That was good news. But that the cover stability was a major concern, particularly on that steep north slope. And in fact, then as part of final design, all of the soil on that north slope was stripped off. It was stripped down to the waist. We anchored geogrids back into the waist. We built up vertical geogrid walls on the benches so we could flatten the slopes between the benches. And then even the soil veneer itself was anchored back into the waste with geogrids. But that's a different story. All right, so building on what I learned from Professor Peck, I wanted to summarize all of this in one 8.5 by 11 page. But in fact, I settled on 2 PowerPoint slides. So what were the lessons that we learned from this project? Well, first and foremost, we learned that municipal solid waste is pretty strong stuff, certainly not characterized by a friction angle of 20 degrees. So it's stronger than often assumed in practice. Also that municipal solid waste can be pretty heavy, that the unit weight is greater than typically assumed. And I didn't mention this, but in the saturated zones, we were getting unit weights on the order of 130 pounds per cubic foot. And that's actually gotten more relevant today as people move towards bioreactor landfills, where they're introducing liquids into the landfill, and I review the designs for these landfills, and they're still using 85 pounds per cubic foot as the unit weight. No, it doesn't, that's not what it's going to be if that waste is saturated. The cyclic degradation of municipal solid waste is relatively slow. We had that upper bound modulus curve. There wasn't a lot of modulus degradation in the earthquake. That increases the potential for amplification of earthquake motions. And in fact, when we first got involved in OII, there was some papers that suggested that, oh, landfills will never amplify earthquakes. Well, and landfills are just like any other earth structure, earth dam. If you have a motion that matches the resonant frequency of your waste mass, you're going to get amplification, and you need to consider that in design. Solid waste is anisotropic. There's a preferred horizontal orientation to the waste, to the structure. That's something that you may want to consider in your stability analyses. And the deformation of the waste is non-homogeneous. So it's good to do monitoring, but I wouldn't get overly concerned if one point showed a sudden increase in settlement. We're still monitoring the deformations of the landfill, and we see that. Occasionally one point takes off, and for a couple of months it really settles, and then it stops and goes slowly again. And so we see very non-homogeneous pattern of deformations. Contributions to practice from OII. Well, the in-situ unit weight testing method. We've now used that on 4 landfills. We've got some really good data on what the unit weight of solid waste is, and we published that in the ASCE journal about a year, I guess 2 years ago now. Field classification system for waste. We've also used that on several landfills. There's a paper that's been submitted for publication to describe that field classification system. We've made some modifications to it since OII, but it's basically that same classification system. We've gotten some good data on waste composition. We found that typically there's a lot of soil and soil-like material in the waste, and that the percentage of soil and soil-like material can influence its properties. And one of the reasons that's important is because landfill owners now are going towards alternative daily covers, where they don't put as much soil on the waste anymore. They'll put tarps on it, they'll take off every night. So the composition of the waste is changing over time as our landfilling practices evolve. We have our MSW shear strength envelope, our bilinear envelope. There's been a lot of other envelopes that have appeared in the literature since then. You know, Tim Stark's got one that's 35 degrees friction angle and 20 kPa cohesion. I like my bilinear envelope. I'm sticking to that story. But I believe that that's a lower bound envelope, too, that the waste can be significantly stronger than that. We learned a lot about the compositional effects on both strength and compressibility of the waste, as well as dynamic behavior. We've continued to build on that with our recent NSF project with Texas and Berkeley. Not only did we get shear wave velocity measurements at OII in this project, but we took advantage of having mobilized the VibroSeis and Professor Stokey, and we took a little bit of money from NSF for post-Northridge investigation, and we went to 7 or 8 other landfills in the Los Angeles region, and we got shear wave velocity profiles for them, and the resulting shear wave velocity profile is still the one that everybody's using for seismic analysis of solid waste. I don't know if there's another one out there. I guess there are 1 or 2 others since then, but that seems to be the preferred shear wave velocity profile. The modulus reduction and damping curves from OII are still the only ones. Those records at OII are still the only records we've ever captured on a landfill in an earthquake. You know, the Peck Award is awarded for published case histories, so I'm pleased to say that a lot of this material has been published, and I have to believe that that was part of the reason that I was given this honor. So here are 5 papers that describe some of what I've talked about today. These 5 papers are solely on OII, but I note that OII data, modulus reduction and damping curves, unit weight curves, shear strength curves, are reported in 17 additional journal and conference papers, 1 California Division of Mines and Geology special report, 1 additional journal paper that's been submitted for publication, and hopefully this Peck lecture when I get around to writing it up and submitting that for publication. So this data is out there for use in practice. Finally, well, not finally, I've got one more acknowledgement after this, but you know, this work was done by a great collection of talented people that I was very privileged to be associated with. And Rudy Bonaparte sent me this picture not too long ago, and this is a great picture of the key members of our team. All the way over there on the right, you see Professor Stokey with his hard hat on. Actually, we all have hard hats on because the health and safety guys were insistent. Next to Ken is Jerry Leonards. As you move along the front row, there's John Christian. In the next row, we've got Rudy Bonaparte, Rick Mitchell, Jim Mitchell, Lloyd Clough, the guy with the white beard, former head of the State Seismic Safety Commission. Bob Backus over there on the left, Nevin Matasevic is in that picture. Missing from this picture, but people who played significant roles in this project include Jorge Zornberg, Gary Schmertman, and Rob Swan from Geosyntec. Well, so in closing, I want to thank the Geo-Institute for the opportunity to present this case history. I want to thank you, the audience, for staying, but most importantly, I want to thank Professor Peck for his great contributions to my professional education, to our geotechnical practice, and my only regret is he's not here to give me a grade on my case history. So thank you very much.